Namaste everyone. Welcome to our YouTube channel Ask Prep. In today's video, we are going to discuss about fusion energy, the holy grail of power generation. Fusion energy has long been hailed as the holy grail of power generation due to its immense potential to provide clean, abundant, and virtually limitless energy. In this comprehensive exploration, we'll delve into the science behind fusion, the challenges of harnessing it for practical energy production, the current state of fusion research, and the prospects for realizing fusion as a viable source of power for humanity's future. Introduction to fusion energy. Fusion is the process by which two atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy in the process. This phenomenon powers the Sun and other stars, where hydrogen nuclei fuse to form helium, liberating tremendous amounts of energy in the form of light and heat. The promise of fusion energy. Fusion offers several advantages over conventional forms of energy generation, including abundant fuel. Fusion fuel sources such as deuterium and lithium are abundant and readily available from sources like seawater and the Earth's crust. Clean energy. Fusion produces no greenhouse gas emissions or long-lived radioactive waste, making it environmentally friendly and sustainable. Safety. Fusion reactions are inherently safe, with no risk of runaway reactions or catastrophic accidents like those associated with nuclear fission. Energy security. Fusion could provide a virtually limitless and reliable source of energy, reducing dependence on finite fossil fuels and mitigating geopolitical tensions over energy resources. The signs of fusion. Fusion occurs when atomic nuclei overcome their mutual electrostatic repulsion and come close enough for the strong nuclear force to bind them together. This requires extremely high temperatures and pressures to overcome the Coulomb barrier and initiate fusion reactions. Fusion reactors. Fusion reactors aim to replicate the conditions of the Sun and stars on Earth, confining and heating fuel to temperatures exceeding millions of degrees Celsius. There are two main approaches to achieving controlled fusion. Magnetic confinement fusion. In magnetic confinement fusion, such as the tokamak and stellarator designs, powerful magnetic fields are used to confine and stabilize the superheated plasma where fusion reactions occur. Inertial confinement fusion. In inertial confinement fusion, lasers or particle beams rapidly compress and heat small fuel pellets, initiating fusion reactions through intense pressure and heat. Challenges of fusion energy. Despite its promise, achieving practical fusion energy has proven to be a formidable challenge due to several technical and engineering hurdles. Plasma instabilities. Maintaining stability and confinement of the superheated plasma is crucial for sustained fusion reactions, but plasma instabilities such as turbulence and disruptions can hinder progress. Energy balance. Fusion reactions must produce more energy than is required to initiate and sustain them, achieving a net energy gain known as ignition or burning plasma. Materials and engineering. Fusion reactors must withstand extreme temperatures, radiation, and particle fluxes, requiring advanced materials and engineering solutions to ensure structural integrity and longevity. Cost and complexity. Developing and operating fusion reactors entails significant costs and technical complexity, posing challenges for funding, construction, and deployment on a large scale. Current state of fusion research. Despite these challenges, significant progress has been made in fusion research, with numerous experimental fusion reactors and research facilities worldwide. ITR, International Thermonuclear Experimental Reactor under construction in France. ITR is the world's largest magnetic confinement fusion experiment, aiming to demonstrate sustained fusion reactions and produce a net energy gain. NIF, National Ignition Facility located in the United States. NIF utilizes inertial confinement fusion to achieve fusion reactions through laser-driven implosions, with applications in both energy research and nuclear weapons stewardship. Private ventures. Several private companies, such as Tokmak Energy, Commonwealth Fusion Systems, and TI Technologies, are pursuing fusion energy research and development with innovative approaches and funding sources. Prospects for fusion energy. While practical fusion energy remains a long-term goal, recent advancements and ongoing research efforts offer reasons for optimism. ITER and future experiments. ITER's successful operation and demonstration of sustained fusion reactions could pave the way for commercial fusion power plants and further research into advanced fusion concepts. Technological innovation. Advances in materials science, plasma physics, and engineering techniques continue to improve fusion reactor designs and address key challenges. Conclusion. Fusion energy represents a transformative and potentially game-changing technology for meeting humanity's energy needs in a sustainable and environmentally responsible manner. While significant scientific and engineering challenges remain, ongoing research and development efforts offer hope for realizing fusion as the holy grail of power generation in the decades to come. With continued investment, innovation, and international cooperation, fusion energy could usher in a new era of clean, abundant, and limitless energy for future generations. Thanks for joining us today. We'll continue making these knowledgeable videos for you in future. Until then, stay curious, stay informed, and stay safe.